Dear students, in the chapter of free damped vibration, today's lecture is on the topic Problems on Logarithmic Decrement. I, Dr. Balraj Singh Brar from Yadavindra College of Engineering, Talwandi Sapo, am presenting the lecture. Usage of logarithmic decrement. Symbol is delta. Logarithmic decrement is used to find damping ratio zeta and damped natural frequency omega d from experimental measurements in an underdamped system. It is valid for viscous damping only. The method of logarithmic decrement becomes less and less precise as the damping ratio increases past zeta 0.5. So usually it gives very good results when zeta is less than 0.5. It does not apply at all for a damping ratio greater than zeta greater than 1 or equal to 1, because then the system becomes critically damped or overdamped. So logarithmic decrement in the use of damping ratio and damped natural frequency from experimental measurements is valid for underdamped systems only. Determination of damping ratio zeta. In the underdamped vibration system, the vibration profile or plot is as shown. Amplitude at the start is at time period 0 is let x. After completion of one cycle, it becomes x2. After 2 cycles, x3, 3 cycles, x4, and so on. And this decrease in amplitude is exponential in nature. And whether we take ratio of x1 by x2 or x2 by x3, these are constant for a vibration system. And from the definition of logarithmic decrement, delta is equal to natural log of x1 by x2, which is equal to, we have already derived in the previous lectures, is equal to 2 pi zeta by under root of 1 minus zeta square. We will be opening up this equation and finding the value of zeta when delta is known. So delta is 2 pi zeta by under root of 1 minus zeta square. Now what we do, we square it and the term becomes, squaring both sides, delta square is 4 pi square zeta square by 1 minus zeta square. By cross multiplying, it becomes delta square into 1 minus zeta square is 4 pi square zeta square. Taking zeta square term on the right side, delta square is equal to 4 pi square zeta square plus delta square zeta square. Taking zeta square term common, delta square is equal to 4 pi square plus delta square multiplied by zeta square. Now taking this term on the other side, we get zeta square is equal to delta square by 4 pi square plus delta square. Dividing numerator and denominator by delta square, we get zeta square, which is 1 by 1 plus 2 pi by delta whole square on simplification. Now taking under root on both sides, we get zeta which is equal to 1 by under root of 1 plus 2 pi by delta whole square, or zeta is equal to 1 by under root of 1 plus 2 pi by natural log of x1 by x2, which is basically delta. This is delta square. So what we have done is we already know the relation for logarithmic decrement, which is equal to 2 pi zeta upon 1 minus zeta square. From this, we will perform the experiment. From the experiment, by observing the ratio of amplitudes, we will be able to find out delta, and once delta is known, we will use this relation to find out zeta, or we can directly put the amplitude to successive amplitudes x1 by x2 if known, and we can find out the zeta from an experimental result. Next is continuing with the determination of damping ratio zeta and damped natural frequency omega t. For values of zeta very less than 1, we have already derived the relation delta is approximately equal to 2 pi zeta. Simplifying it, what we get is, we get zeta is approximately equal to delta by 2 pi. So from any two successive amplitudes, or from a ratio of amplitudes after n cycles, we can find out delta. Put in this, we can find out zeta for a vibration system. And damped natural frequency of underdamped system omega d can be found out from this relation. We know the relation under root of 1 minus zeta square omega. Omega is natural frequency, which is found by taking under root of k by m, and zeta from relation from previous derivation, it is put here, and we are able to determine omega d from an experiment in this way. Damping ratio zeta for n cycles. Suppose we know amplitude at the start of the vibrations, which is x1, and say we know amplitude after 4 cycles, which is x5. Then we can find out, logarithmic decrement delta, which is equal to 1 by n natural log of x1 to xn plus 1, means after n cycles. In the present case, say after 4 cycles, it will be x5. And we already know delta is 2 pi zeta upon 1 minus zeta square. We can find out delta from this relation, observing x1 and xn plus 1 from experiment. We will put in this, we will find out zeta, same relation. Or if we want to put the values of first amplitude at the start of the cycle, and amplitude after n cycles, here n is the number of cycles, then we can use this relation. Simply we have done is we put the value of delta from here in this relation to derive the relation for zeta. So in the coming slides, we will be applying these relations to solve different problems. Problem first is, let we have a vibratory system, which is a spring of stiffness K, mass mkg, and damper of damping coefficient C. In this case, it is given that a vibratory system consists of a mass of 10 kg, spring of stiffness 1000 Newton per meter, and a dashpot with damping coefficient of 20 Newton second. So now we have to determine the value of logarithmic decrement delta and ratio of two consecutive amplitudes, say x1 and x2. So we have to determine delta and x1 by x2, given is mass 10 kg, stiffness 1000 Newton per meter, and damping coefficient 20 Newton second meter. Now, first of all, finding the critical damping coefficient, for which the relation we already know is Cc. Critical damping coefficient is 2 times 1 root of Km. Now putting the values of K, 1000 Newton per meter, mass 10 kg, we solve it to find out Cc, which is 200 Newton second per meter. Then from the definition of damping ratio, zeta is equal to C by Cc. So we put the value of C, 20, Cc value we have calculated, which is 200, and on solution it gives us zeta value of 0.1. So from the definition, logarithmic decrement delta is 2 pi zeta upon 1 minus zeta square. We put value of zeta 0.1, simplify, and delta comes to be 0.628, which was to be calculated. Next is, we know logarithmic decrement from definition is natural log of x1 by x2. So x1 by x2 is equal to e raised to power delta. We put value of delta here, which is 0.628, and we solve, and the ratio of successive amplitudes become 1.8738. So we are able to find out the ratio in which the successive amplitudes will be reducing for this experiment. Moving on to second problem. Again, in a spring mass damper system, free vibration record of a 500 kg machine mounted on an isolator. Isolator is having a stiffness and damping is such that the initial amplitude is 6 mm and the amplitude after the completion of 4 cycles is 0.2 mm. Time period which has been observed for damped vibrations is 0.5 second. Identify the type of isolator, its characteristics, spring stiffness, damping coefficient, and so we are given mass is 500 kg, x1, initial amplitude before the start of vibrations is 6, after 4 cycles fifth amplitude is 0.2, number of cycles are 4, time period is 0.5 second. We know initial amplitude is 6 mm. After 1, 2, 3, 4 cycles, fifth amplitude is 0.2 mm. Now, from a relation of logarithmic decrement where the amplitudes after n cycles are related, we have logarithmic decrement delta is equal to 1 by n natural log of x1 by xn plus 1. Now, from this relation, putting value of x1 6, xn plus 1, which in this case is x5, and n value 4, we calculated delta, it came out to be 0.8503. Now from the relation of damping ratio zeta already derived in today's lecture, it is equal to 1 by under root of 1 plus 2 pi by delta square. Now putting the value of delta 0.8503, we observe that zeta comes to be, damping ratio comes to be 0.134. It is quite less than 1, and usually this is an underdamped system, and very good results we get for less values of zeta. We have calculated zeta, which is 0.134. Now we will be calculating damped frequency omega d, for which the relation is 2 pi by Td. Td is the time period for the damped vibrations, and for the present case, experimentally it has been found to be 0.5 seconds. We put it here and saw omega d becomes 12.566 radians per second. We know omega d is under root of 1 minus zeta square times omega n. From this, omega n becomes omega d by under root of 1 minus zeta square. We put value of zeta 0.134 as calculated, omega d 12.566. We solve, natural frequency comes to be 12.681 radians per second. We know relation for omega n is under root of k by m, from which k is m omega n whole square. We put value of m 500 kg, omega n 12.681. We have calculated, we solve, and now we know the stiffness of the spring mass damper system from the profile. Solving it, it comes out to be 80,403.88 Newton per meter. Critical damping coefficient is 2 times under root of km. K we have solved, m is given. This becomes 12,681 Newton second per meter. And from the definition of damping ratios, damping coefficient is equal to damping ratio zeta times the critical damping coefficient zeta. We have calculated 0.134, and critical damping coefficient is 12,681. We saw, and we know damping coefficient for the system is 1699.25 Newton second per meter. Continuing to the problem number 3, it is given that the equation of motion of a harmonic oscillator is d2x by dt square plus 2 zeta omega n dx by dt plus omega n square x is equal to 0. where d2x by dt square is acceleration, zeta is damping ratio, omega n is natural frequency, dx by dt is velocity, omega n again natural frequency, x is the displacement. Initial conditions are given at time is equal to 0. Initial displacement is capital X and velocity at time is equal to 0 is 0. It simply means that at the start of the time, the system is at one of the extreme positions and the amplitude x is the maximum amplitude of the vibration. Now we have to calculate amplitude xt after n complete cycles. So we are given that x1 at the start of the vibrations is equal to x1 is kept x maximum, which is x, and we have to calculate xn plus 1 after n cycles. We will be solving in the coming slides, and the correct answer is A, which we will be proving, which is equal to capital X e raised to power minus 2n pi zeta by under root of 1 minus zeta square. Now, differential equation given is d2x by dt square plus 2 zeta omega n dx by dt plus omega n square x is equal to 0. We solve this. We put value of zeta, from definition it is C by critical damping coefficient, and value of omega n is K by m under root, and omega n square is K by m. Then we put value of Cc is equal to 2 times under root of Km, and on simplification 2's cancel out, under root k cancel out in the numerator and denominator, multiplication of under root m and under root m yields m, and k by m is as it is. Multiplying this equation by m on both sides, we get m d2x by dt square plus c dx by dt plus kx is equal to 0, which is the standard differential equation for a spring mass damper system. Spring mass damper system. So, as we discussed, amplitude as given at time is equal to 0, dx by dt is 0, so it means at time is equal to 0, displacement is maximum and is amplitude of the vibrations and is denoted as x1. Now, underdamped system will have profile like this, and first amplitude is x1. Say after first cycle, second amplitude, third, fourth, fifth, we want to find out after n cycles xn plus 1 amplitude. So from definition, logarithmic decrement is 1 by n natural log of x1 by xn plus 1. Solving n delta becomes natural log of x1 by xn plus 1. x1 by xn plus 1 becomes e raised to power n delta. Now putting value of x1 equal to capital X maximum amplitude, xn plus 1 is capital X e raised to power minus n delta. We know delta is 2 pi zeta upon 1 minus zeta square. We put delta here, amplitude after n cycles, n plus 1th amplitude becomes x e raised to power minus n 2 pi zeta upon 1 minus zeta square, which on solution gives capital X e raised to power minus 2n pi zeta upon under root of 1 minus zeta square, which is the first choice as given in the problem. With this, in the present lecture, we have applied the relation of logarithmic decrement to solve different problems. Thanks for the patient hearing.